afternoon, everyone. So, in this particular work, we will talk about how to design an accelerometer based on the curve beam. So, the outline of my presentation will be like until now, how the beams are being used for the accelerometers, and then the important thing is that if we want to use curve beam, we need to first understand how the curve beam frequency basically varies with the parameter and how to write the governing equation of that. So we have first done that modeling and then compare it with simulation from console. And after that, we have utilized the curve beam in designing our accelerometers, which is in plane accelerometers. And then we have performed static and mode analysis, and afterwards, closed loop analysis for converting displacement to the voltage using MEMS plus this Simulink model. So if you see, accelerometer finds many different applications, starting from mobile to aerospace, and the types maybe from piezoresistive, capacitive, tunneling, optical, and piezoelectric. In this particular talk, we are focusing more on the capacitive type. So these are some of the recent application of the curve beam. If you see, like a low G kind of accelerometer where there are the curved structures like this, where you can even decide how many you want to use it. And in the first design, you can see only 3 curved structures are being used, where anti-spring concepts are being used in this case. And then you have other structures where such kind of like such kind of structures are being used more and more in the recent case. So to know how to first of all obtain the equation for curving, so of course, like under the assumption of a small displacement considering Euler beam theory, and then in extensional theory, where we are so we can write the equations which is mentioned over here in terms of the variable along the curve. So alternatively, you can also write this in terms of the sector angle, this particular equation. So if you just see that, I'll just get the mouse. Pointer. Yeah. So if you see, this is your sector angle, and the S is along this particular curve. So either in either form. So if you try to see the relationship, this is what you get here. So the same equations can be rewritten in the form of theta, and then we can assume the solution in this form, and then find out this linear equation. And afterwards, we can do eigenvalue analysis and find out the eigenvalues and the corresponding mode shape. So for getting the same thing, for example, if you when you are using curve beam with your proof mass, so proof mass is basically going to move like this. So you don't have literally the cantilever, but the guided cantilever kind of condition happening. So it is not just bending like this, but there is also something which is extending, and then R is also changing. So those kind of, so it means we need to be very careful what kind of conditions we are going to use. So these are like curved cantilever, simple supported, clamped, and the guided curved cantilever. After that, we found the frequency equation following the same approach for all these conditions, and which you can solve to find out the mode shapes and as well as the frequencies. So this is just the comparison with analytical and numerical, where you can see that we have pretty good variation or match with analytical and numerical for cantilever, fixed, and simply supported, but there is still a little bit of variation we can see in the guided cantilever, which needs to improve, but more or less they are quite near. So based on that, we utilize that to model our accelerometer. So here we are taking a proof mass, and which is around 2000 into 500 micrometer. and then four curved cantilever beams. And after that, we are modeling it in MEMS Plus, where you can select the material, you can select the process of SOI, and then different components which will make this particular um, um, design, and then you can do the analysis and uh, create the MEMS plus model. So this is your 3D kind of structures where you can see the thickness is 25 and then handle wafer is 400. So now when you see the change in the frequency of this particular structure with the uh, thickness, you can see that the in-plane and out-of-plane motion frequencies are quite near when the thickness is small, and as it increases, of course, the stiffness in one direction will be different from the another. So that way, your frequency here will increase further. So especially in the out-of-plane motion. And same way, if you try to see the radius of curvature, so with respect to that also for the smaller radius of curvature, you have higher frequencies, and as it increases, so both the modes will come quite close to each other. After that, we did static analysis where we varied G from minus 10 to 10 and found out the changes in the displacement uh, at different radius of curvature. So here you can see for large radius of curvature, we get more displacement. However, while varying this curve beam, the variations, if you can control this displacement limit also over this G, and the corresponding capacitance change that you can also achieve from approximately minus 250 to 250, so like a 250 femtofarad. And based on that, if you design the sensitivity based on displacement and capacitance, you can see that with the increase in radius of curvature, you can increase the sensitivity. And so when you take the thick beam, there whenever you go to the DRI process, there is a possibility of getting the thickness inclined. So it doesn't remain same, but inclines. So because of this inclination, we have fabrication defect. So when we design, those things also needs to be taken care. So here that wall variation is being changed from, you can see, -1 to 1, and the corresponding frequency change, you can see around 12% that will come, and even quality factor basically from the combs. So this is here, if you just see, there are combs over here. One is fixed comb, another one is free, and it moves this way. So these two combs will, combine like this, and it will create a squeeze film damping kind of dissipation. So that will also vary with these side also that we have also calculated and found the variations. Then stresses, which turns out to be 0.57 megapascal. Sorry for the mistake. So which is quite less than the yield. So it is safe. We also found that because of the curve beam, the bandwidth can also be increased. And so after looking at this mechanical analysis, we uh, took the model from MEMS Plus, this lump model, where all the like parameters are there in MEMS Plus analysis, and the output will be given out, and it will be interfaced with the Simulink, where we have designed this capacitor voltage conversion. And for two kinds of input, like if the accelerometer is varying from -10 to 10 in sinusoidal form and in ramp step input form. So you can see that you have variations which are in the, this is the net capacitance. Basically, you have two sets of combs. One is like one comb will come towards fixed one, another one will go away from the fixed one. So that's why you see that they are opposite to each other, and the combined is the one that has to be measured. So that works. What so so it means the open loop analysis for all we have done for these two cases. Further closed loop analysis needs to be done. So conclusion is curve beam is basically, there are many applications, and including in the MEMS, where we have shown how it can do the changes in different characteristics. And then this analysis also shows that we can also, so basically we can use this for the low G kind of application. So with this, thank you very much for your attention. These are the references and acknowledgement to my students and the idea for the project.